Hello everyone. In this lecture, we are going to talk about some laws pertaining to the relational algebra expressions. So, two relational algebra expressions are said to be equivalent if those two expressions generate exactly the same set of tuples on every legal instance of the database, right? Uh, Now, what we are going to do is that we are going to cover some set of equivalence rules, and these equivalence rules, what they tell us is that they are a little bit more formal in telling you, they will help you to derive, which relational algebra expression is equivalent to what, right? And just to give you a little bit of a disclaimer here, so the set of equivalence rules which I am going to cover here, they are theoretical certainly, but their actual use is being done at the query optimizer level. So when you are writing relational algebra expressions, you don't have to worry about whether your expression is optimized or not, right? So your a relational algebra expression, it should be correct. It should have all the semantic values and it should be correct. Whereas these laws which we are going to cover in this lecture, they are actually used by the query optimizer to generate equivalent relational algebra expressions, and it is mostly used for performance. But nevertheless, I'm covering this set of slides here so that you can appreciate the complexity which goes into a query optimizer, right? And also you should be able to appreciate that whatever things are done at the system level, there is actually a firm theoretical base towards that, right? Okay, without any further delay, let me start going deeper into these equivalence rules. Okay, so the first set of rules, they are pretty straightforward. The first one says that if you have a relation E and then you are passing that relation through an select operator, and that select operator consists of two Boolean expressions, theta 1 and theta 2. If you have something like this, then it means that you can break this and you can pass the relation E through, maybe let's say theta 2 first and then theta 1, right? So you can sort of break a set of Boolean conditions given in a select operation, something like this, right? So this is pretty intuitive. I don't think I need to explain it much more deeper. Right? The second is also quite intuitive. So here what we are saying is that if you have a relation E and you are passing it through theta 2 first and then a select operator with theta 1 condition. If you have something like this, the select operations are commutative, right? So instead of passing E through theta 2, you may want to pass it through theta 1. So this operation, this rule is extremely used by your query optimizer. The way it uses is that if you are giving two conditions, theta 1 and theta 2, on a relation, what it will do is that it will check which of these two conditions is easier to apply, or which of these two conditions would result in a far fewer tuples, right? So something, it does all those kind of things, and then it even changes the order in which these select operations are performed, right? So query optimizer is smart in that sense. Now the third one, again, this is also pretty self-intuitive. So if you have a relation E and then you pass it through a set of or a sequence of pi operations, projection operations, then it really does not matter what projection operations you are keeping here. Only thing that matters is that what is the final projection operation, right? So these two expressions, they are equivalent. That's what I was saying, right? The previous slide also, when I use the word equivalent, uh, what I meant is that on this side, the right hand side relational algebra expression, this is equivalent to the left hand side, and similarly is the case with this rule and this rule, right? Okay, now the fourth one over here. So I think this I have covered even before also. So if you have a theta join between E1 and E2, that can be simply written as you perform a cross product first and then you perform a select operation. I think for A we have covered multiple times in the previous videos, right? And then similar is the case over here also. So this guy says that if you have two relations E1 and E2 and you're doing a theta join between E1 and E2, and then from the over whatever is the output after that, you are passing the output through a select operator which has a boolean condition theta 1. So if you have something like this is equivalent to performing the theta join between E1 and E2, where the join condition is itself an it's basically a combination of the theta 1 and theta 2, right? So you, if you have something like this, you can use it just in conjunction of both theta 1 and theta 2 over here. Okay, so again, few more intuitive things here. uh, Theta join operations are commutative, right? So E1, whether you join E1 with E2 or E2 with E1, right? So the result is same, and similar is the case with natural joins. Again, pretty straightforward. And natural joins are associative. Means if you are joining E1 with E2 and you are joining the result with E3, this is same as you join E2 with E3 first and you join the result with E1, right? And again, this is also extremely used inside a query optimizer. If you are joining, three tables, then the query optimizer will try to figure out that, which of the joins would result in a smaller intermediate table, right? So if E1 and E2 results in a smaller size of the intermediate table, then the query optimizer will pick this first, right? So just again, as I said, it's a way to appreciate, what all goes inside a query optimizer, and to realize that, there is a firm mathematical background behind that query optimization, which is done in modern databases. Okay, so another example here says that theta joins are associative in the following manner, right? So the way to read this expression is following. So you have on the left side, you are joining E1 and E2 using a theta join, and the join condition is theta 1. Okay, and the resulting you are joining with E3, and the result contains the Boolean expressions theta 2 and theta 3, right? So if you have something like this, you can break it, or you can decide to join E2 and E3 first and then result with E1, right? So here, for this expression, we are making some small assumption that if theta 2 is the set of attributes which are only from E2 and E3, right? Then E2 and E3 can be joined using this theta 2, and you can join the result with E1 using the uh, uh, conjunction of the expressions theta 1 and theta 3. Okay. So when you are using this rule, you will have to be little bit careful. You have to carefully see what is theta 1, theta 2 and theta 3, right? Otherwise you may make some mistakes over here. So here, there was, as I said before, there was a small assumption that when you are joining E2 and E3, all the required conditions which are, semantically meaningful for you, for that particular query, they are encapsulated in theta 2, right? And then similarly, this theta 3 came here, right? So don't apply this rule blindly. You have to be little bit careful in what is theta 1, theta 2, theta 3, and then you have to sort of arrange these expressions accordingly. But nevertheless, I guess you get the overall picture that whenever you have three tables joining like this, you can do associative way. That means in that either you decide E1, E2 to be joined first, or you join E2, E3 to be joined first, and things like that. So that's okay. I think at this level, this is just an illustration of the previous slide. Okay, more equivalence rules. Okay, so here we say that a selection operation distributes over the theta join operation. Right? Now let's see what does it mean. Right? So here you have two cases. In the first case, I say that when all the attributes in theta 0 involve only the attributes of one of the expressions in E1. Right? So you have two tables, E1 and E2, and you are performing an theta join between those two, and then you have another select operator outside them which has the condition theta 0. Now here what we are doing is that we are saying that theta 0 contains attributes which are only from E1, right? So if such is the case, what has happened is that you have sort of pushed this theta 0 into E1, and then you are joining the result with E2. So in other words, I am first performing the select operation E1 and then joining with E2. And again, this can work only if theta 0 is containing attributes only from E1. Otherwise, this is not valid, right? Again, this is also extremely used in a query optimizer, right? So if you have conditions like this, then what the query optimizer will do is that it will smartly perform the select operation on E1 first, so that you get a slightly smaller table, and using that smaller table, it will join with E2, right? So so these kind of tricks are used by the query optimizer. Right? Again, I think the B rule is just an extension of this. So here, what we are doing is right. So again, you have a join between E1 and E2. It's a theta join. The join condition is theta over here, and whatever result comes out of it, you are passing it through a select operator, which comprises of two Boolean conditions, theta 1 and theta 2. We say that theta 1 is containing attributes only from E1, whereas theta 2 contains attributes only from E2. So if you have something like this, you sort of push the select operators inside, right? So for example, this sigma theta 1 got pushed onto E1, and this sigma E2 theta 2 got pushed onto E2, right? And then whatever is the result, you perform an theta join. Again, pretty intuitive. Here, basically what we are doing is that we are decreasing the size of E1 and E2 before the join operation. Again, very widely used tool, right? So query optimizer does all these things. And the reason we do this is because the join operation is typically computationally more extensive, right? So we always try to minimize the size of the tables which are going into the join operation, right? So these kind of things are done. Okay. Next. Okay, so here is another rule. So this one is slightly more complicated. So let's go through it slowly. Okay, so you have two relations E1 and E2, and you are performing an join, theta join between E1 and E2. So E1 theta join E2, and then over the result you are performing an uh, projection operation, and the list of attributes in this projection operation is L1 union L2, right? So now what we are saying is that the theta happens to be whatever Boolean expression theta is, it happens to contain attributes which are present in L1 union L2, right? Remember that E1 and E2, they can have whole lot of attributes, but finally in this particular case, what is happening is that my final projection attributes in the final projection, which is L1 union L2, they happen to be such that they cover all the required attributes which are there in my theta. So, if such is the case, what we are doing is we are first projecting E1 on L1 and then projecting, almost simultaneously projecting E2 on L2 and then performing the theta join, right. So, again here what we are doing is we are basically reducing the size of the relations going into the join operation. So, in the previous slide, here when we are doing something like this, we were slicing the table, we were reducing the size of the tables by removing some unnecessary tuples, right. So, here that was happening over here, right. So, when we had the sigma theta 1 and theta 2 and we are going through this join, I push the select operation here and push the selection operation here. So, here we are in this case, we were reducing the size of the table by removing some unnecessary tuples, right. So, that was done here. In this particular example, what we are doing is we are also reducing the size of the tables here, but here the reduction is coming from the columns wise. We are removing some unnecessary columns which are clearly not going to be used at the final result, right. So, the previous slide, that was we were reducing horizontally. Here we are slicing vertically, right. So, so we are removing unnecessary attributes which are not going to be in the final result, right. So, so the, and for this to work, the primary condition is that this theta 1, this theta join condition, this should contain attributes which are present in this L1 union L2. If only if things like that is happening, then you can push the corresponding projections inside and do the join operation later. Otherwise, this will be mathematically incorrect, right. So, as I said, the way to interpret this rule is that you are slicing the table vertically by removing some unnecessary columns, whereas in the previous case you were slicing the table horizontally by removing some unnecessary rows. Okay. Okay. So, and I know 8b is a slightly more complicated version of this. So, here let's just quickly read this definition here. What we have is we have some set of attributes L1 and E2, L1 and L2, which happen to be attributes coming from E1 and E2. Note that L1 is not the complete set of attributes of E1. E1 can have many other attributes, right. These are just some attributes, right. And and the way this L1 and L2 are defined is that they are the attributes which are going into the final projection. Okay. And two more definitions. So, let us say that L3 is the set of attributes that are actually involved in the join condition, this join condition, but they are not present in L1 union L2, right. So, that is L3, and then similarly L4 are the set of attributes from E2 that are involved in this join condition T2, but they are not present in this L1 and L2, right. So, here what we are going to do is we are going to do projection of E1 and E2 such that the join the tables which are going into the join operation, they are smaller in size. Now, previously, we projected entire projected E1 onto L1, but here we are not able to do that because this join operator theta contains some other attributes of E1 which are outside this L1 union L2, and similarly this join operator theta contains some other attributes of E2 which are not fully covered in this L1 and L1 union L2. And so, now what we are doing is we are projecting E1 on to the set of attributes which is L1 union L3, right. And then similarly we are projecting E2 on a set of attributes which is L2 union L4, right. Recall that this L3 and L4, they are the set of attributes which were outside this L1 union L2, but they were involved in this theta join, right. So, we are just being smart about what is the smallest possible E1 that you can create, or what is the smallest possible E2 that you can create to send it into the join, right. and from the setting that we scenario that we developed here. So when you project E1 on L1 union L3, and then when you project E2 on L2 union L4, then you have the bare minimum required information from E1, and you have the bare minimum required information from the E2 for you to successfully perform this theta operation, and then again perform this pi operation over L1 and L2, right? So you can take a simple example and sort of convince yourself that this is indeed the case, right? Again, intuitive, don't try to mug up anything here, it will not work out. They are intuitive, you take some little examples, work it out if you are getting a little bit confused, right? And if you have any doubts, please do email me, we can go over it in the live session and all that, right? But don't try to mug it up, there is an these are intuitive expressions. These rules are highly intuitive. You just have to sort of give it some time to fully absorb it. There is no magic going on here. Okay. Okay, so now we are going to cover some simple examples to show how those equivalence rules which we covered just now, how they are used in actual practice, right? So more of this will happen when we are doing query optimization, but just to give you a gist that how query optimizer uses these rules to get an execution much more faster. Okay, so here in this case, we have let's say three tables: branch, account, depositor, and you are performing a relational algebra expression, something like this. So you join account with depositor. I think it's natural join, and then the result you join with branch. You perform a select operation where branch city is equal to New Delhi, and then finally project out, let's say, customer name, right? So don't go into the semantic meaning of this expression. You just take this as its face value, that you have an valid relational algebra expression. Now let us see how we can try to execute it quickly, right? So using one of the transformations, you might remember that whenever a select like this is there, let's say that this branch underscore city, this attribute, this is, let's say, valid for branch table, right? It's quite intuitive. So in this case, what we are doing is that we are pushing this select condition onto the branch, so that whatever table that has to be joined with this result of account join depositor, that size reduces, right? So if you perform this particular select operation onto the branch first, then you get a smaller intermediate result, and that can probably be joined with this result much more easily, right? So just to illustrate, let's see, I think I have one more example. Okay, so now we have let's say something like this, right? So here what we are doing is we are joining branch with account, and then you are performing this select operation over here, and whatever is the result, you are joining it with depositor, and then finally you are projecting on customer name, let's say, right? So here some assumptions here. So let's say that after you do this join branch natural join account, let's say that after you do this, you get a schema like this, right? Branch name, branch city, account type, account number, and so on, right? So if only few attributes of this intermediate relation are going to be used in the next join, then you can change it a little bit, right? So you can be a little bit more efficient here. I think I have the expression. Yeah. Okay. So here the assumption is that okay. So here the assumption is that the account number is being used next. Okay. So there is a small bug here. So you should not put this here. Okay. So the assumption is that in the in from the intermediate relation which we get over here, and after performing this portion of the query, out of this, let's say that only account number is being used or would be used for the for the join operation with the depositor relation. And none of this is actually sitting in the pi. So when you have something like this, what you can do is you can perform the pi operation here, right? You're sort of pushing an pi into this, into here, right? So we do this join, you get an intermediate result, and then you sort of project it onto the attribute which is actually relevant for the next join, right? So here also, moral of the story is that we are trying to be smart in reducing the uh, size of the tables which are going to be used in the join. That's what this is all about, right? So that is why all we are pushing select conditions inside sometimes, or we are putting some extra projection attributes, right? So the whole story is centered around the fact that we want to reduce the size of the tuples which are going into the join operation, and we use all of our previous equivalence rules which we covered to do this, right? And I think I have said this multiple times before that that these things are actually used in the query optimizer. So if you give an SQL query which is something like this, or if you give a query which is something like this, it can automatically figure out that that this is the most efficient way of executing that query all by itself, right? So this is the beauty of a query optimizer, or the amount of engineering which goes into that. So when you are writing a relational algebra expressions, you don't have to worry about the performance. So that is the primary benefit of a database system that it gives you, right? So when you are writing an SQL query, you don't worry about what is the performance of that for the largely most of the cases, right? And the query optimizer automatically figures out that for your SQL query, which you are writing it in high level language without worrying about, what is the most efficient way of solving, the query optimizer can do all of these, massaging and, figuring out of the query plan without you having to worry about. This is the primary reason why database systems became so popular, and the fundamental people who are involved in this, they both got Turing awards, right? So this gives a very wonderful division of the logical model and the physical model. So at logical state, when you are defining your business requirements using these operators, you absolutely did not have to worry about whether this is going to be the most efficient way of execution or not. The physical model takes care of it. And why it is able to do that? Because because all of your business logic was written using just a couple of operators, and all those operators follow a standard set of equivalence rules, and a standard algebra is being followed, right? So that is the whole beauty of a database system. That is why these things became so popular, right? So the relational algebra and all its equivalence rules, they are used by the optimizer to figure out a perfect query plan without you having to worry. Largely, that's the case, without you having to worry about how to write an efficient query. Right? I think my slides. We have one more example here, but more of this will happen when I cover query optimization. Okay, so I think I'll stop here for this lecture.